At first glance, playing games in virtual reality, VR, might seem like pure entertainment, a novelty that's fun, maybe even distracting. But beneath the surface of these digital experiences lies a profound scientific frontier: immersive brain training. As VR technology becomes more advanced and accessible, neuroscientists, psychologists, and educators are discovering that stepping into virtual worlds can fundamentally reshape how we learn, adapt, and think. Imagine this. You put on a VR headset and suddenly find yourself navigating a rescue mission, managing a spaceship's energy systems, or escaping a burning building. You're solving puzzles, multitasking under pressure, and making split-second decisions. But here's the catch. Your brain doesn't fully distinguish between real and virtual experiences. The sense of presence is so powerful that it engages the same neural circuits as if the challenge were happening in real life. That's the magic of VR. It doesn't just show you information, it puts you inside it. And because it activates multiple sensory modalities, vision, sound, proprioception, sometimes even touch, VR can train the brain more effectively than traditional 2D media. You're not just reading about spatial reasoning or memory tasks, you're living them. But how exactly does VR improve cognitive skills? One major area is problem solving. In immersive environments, users are often faced with complex, open-ended challenges: how to navigate an unfamiliar terrain, how to manage limited resources, how to respond to unexpected obstacles. These experiences stimulate the prefrontal cortex, the brain's center for planning, decision-making, and cognitive flexibility. Studies have shown that after repeated exposure to such virtual challenges, participants often exhibit enhanced real-world problem-solving ability. They become more adaptable, more resilient under stress, and quicker to identify patterns and solutions. Another domain is spatial awareness and memory. Traditional brain training exercises like memory games or logic puzzles are often abstract. VR makes them concrete. You might be asked to memorize the layout of a maze or track multiple moving objects in a 3D space. This type of engagement taps into the hippocampus, crucial for spatial memory and navigation. Research has found that VR-based training improves recall not just in the virtual world, but in real environments, particularly in older adults, people recovering from brain injuries, and even those with early cognitive decline. Want to enhance your focus and attention span? VR is being used to create immersive meditation and neurofeedback experiences that teach users to regulate stress, stay present, and manage distractions. The brain learns to tune into relevant stimuli while ignoring noise, an essential skill in our fast-paced, notification-saturated world. You might ask, does VR training really translate to the real world? That's the key question, and the answer is increasingly yes. Because VR creates embodied experiences. You move, act, and feel consequences. It creates stronger memory traces and faster skill acquisition. For example, surgeons trained in VR perform better in operating rooms. Athletes who visualize and rehearse movements in VR show improved physical performance, and children with attention challenges show gains in executive functioning after immersive cognitive games. Even more intriguing is VR's potential to train adaptability itself. In rapidly changing environments, the brain must learn, how to update its models, adjust behavior, and stay flexible. By exposing users to unpredictable, high-stakes scenarios, VR can simulate real-life uncertainty in a safe, repeatable format. Think of pilots in flight simulators, soldiers in combat training, or emergency responders navigating chaotic disasters. In each case, VR helps prepare the brain not just to perform tasks, but to adapt under pressure, a core element of human intelligence. And what about long-term effects? Early evidence suggests that immersive cognitive training may even promote neuroplasticity, the brain's ability to rewire itself. This is especially important in stroke recovery, age decline, or trauma rehabilitation. VR offers a controlled, customizable environment where users can gradually rebuild cognitive and motor functions at their own pace. With real-time feedback, But with such powerful tools come new questions. How do we measure cognitive gains across individuals? What ethical safeguards are needed when training attention or emotion in immersive settings? Could VR-based cognitive enhancement one day create unfair advantages or even change how we define education and intelligence? For now, the answers are still unfolding, but one thing is clear: immersive VR isn't just a game. It's a neuroscientific interface, a platform that lets us sculpt the brain through lived experience inside artificial worlds. It could reshape how we teach, how we heal, and how we prepare minds to thrive in a world of accelerating complexity. And perhaps that's the most exciting part, that by donning a headset and stepping into a virtual challenge, we're not escaping reality, we're training to master it. Immersive brain training through virtual reality, VR, refers to the use of digitally created, interactive environments to stimulate and enhance cognitive processes by simulating complex, dynamic, and sensory-rich scenarios that engage multiple cognitive domains such as attention, memory, spatial awareness, and problem-solving. A VR platform designed for surgeons, for instance, provides an interactive 3D anatomy simulation that allows users to practice procedures in high-pressure environments mimicking real-life operations, much like rehearsing a play in a fully built set rather than simply reading lines from a script. The brain learns the role much faster and more deeply when immersed in context. Cognitive engagement in VR environments is defined by the system's ability to stimulate neural pathways involved in perception, memory encoding, motor planning, and executive function through immersive interactive spaces that activate both sensory and motor cortices, thereby facilitating embodied cognition. In a VR training module for firefighters, users must quickly assess structural integrity, identify hazards, and coordinate movement under time pressure to improve executive decision-making and risk assessment. Much like playing chess on a battlefield, where each move is learned not in the abstract, but through lived experience and immediate consequences. VR enhances cognition through mechanisms such as situated learning, embodied interaction, contextual memory encoding, and feedback-driven neuroadaptation by allowing real-time modulation of complexity, difficulty, and personalized feedback loops. Cognitive rehabilitation programs, for example, use VR to simulate urban navigation tasks for stroke patients, gradually retraining memory, orientation, and planning skills in adaptive, gamified environments. Much like teaching someone to swim not by reading a book, but by gradually immersing them in water with customized support and challenges. Immersive brain training demonstrates principles of complexity science by viewing cognition as an emergent property of interacting subsystems, visual, auditory, motor, and decision-making, that can be simultaneously probed and trained in real time, uncovering latent capacities or deficits. Military VR simulations, for instance, train soldiers in unpredictable, high-stress environments to enhance real-world decision-making, teamwork, and resilience. Much like training a pilot in a flight simulator during turbulence, where one learns to think rather than just follow preset procedures when systems deviate from the norm. Brain training in VR alters energy distribution and activation patterns across neural networks by increasing metabolic activity in regions such as the prefrontal cortex, hippocampus, and parietal lobes, thereby supporting synaptic strengthening and cortical reorganization, crucial for long-term cognitive enhancement and recovery. Elderly participants engaged in VR-based memory games have shown increased connectivity between hippocampal and frontal regions, correlating with improved recall performance, much like using a spotlight to awaken dormant parts of the brain. Each scenario acts as a bright flash that draws attention and energy to previously neglected circuits. Virtual reality environments facilitate multimodal learning by encoding information through combined visual, auditory, and kinesthetic stimuli, which strengthens memory traces and promotes long-term retention through episodic memory formation. In language learning scenarios, navigating a virtual city, ordering food, and responding to local customs leads to improved fluency and context-anchored recall, much like learning a language by traveling to a new country, where the words stick because they are inseparable from the experiences encountered along the journey. Immersive brain training is reshaping neurorehabilitation, education, and human-machine interaction by enabling experiential learning that helps users grasp complex concepts by living through them, while also offering platforms for training AI agents in human-like decision-making through embodied, simulated tasks. VR classrooms, for example, allow students to explore historical events, physics simulations, or molecular biology by manipulating virtual objects, engaging deeply with abstract content, much like shrinking students and placing them inside a cell where they can explore mitochondria not as static charts but as dynamic walkthrough structures. While immersive brain training holds immense promise, challenges remain in ensuring that the skills acquired in virtual environments transfer to real-world contexts, mitigating sensory overload and avoiding cognitive fatigue. A VR game that improves visual attention may not automatically enhance verbal memory unless the tasks are designed to integrate multiple cognitive domains, much like learning to drive in a video game might teach steering, but without real traffic or weather feedback, the learning remains incomplete. The future of immersive brain training lies in neuroadaptive VR, where brain signals such as EEG or FNIRS dynamically influence training content, and integration with AI allows for real-time personalization that optimizes challenge levels and stimuli based on neural engagement. Startups are developing VR headsets with integrated biosensors to monitor cognitive fatigue and adjust difficulty to maximize neuroplasticity. Much like having a personal trainer inside your brain who senses when you're ready to level up and adjusts the surrounding environment to build your mental muscles.